Okay, welcome back everyone for the afternoon session. The first talk of this session is by Hiroyuki Katsura from University of Cambridge. And he'll talk about combining agentic AI and lightweight formal methods to find bugs in a production hypervisor.
Yes. Thanks for the introduction. I'm Hiro. This is a joint work with Kayvan, Memarian, and Peter Sewell. So basically, this talk is about combining agentic AI and lightweight formal methods to find bugs in a production hypervisor. More precisely, what I did is we asked OpenAI Codex to write executable test specifications in the ambient language, following the framework by Memarian et al., and then for the Android pKVM hypervisor. And then we found several amusing bugs. But probably this slide doesn't make sense to you until we explain this part. So I would like to start with talking about what is writing specification in the ambient language first. The high-level idea here is that what we want to do here is to write nice specifications. And the specification and implementation is a sort of two different redundant views of the things, and then tensioned against each other. And then especially if you only have an implementation with no specification or with some very prose specification, what do we do for this? One possible thing that we can do is to do some formal verification. And then this is actually good if you can actually do this successfully, because you can get a very strong guarantee about the implementation. But the thing is that even in the era of LLMs, especially retroactively verifying something is very difficult. And then possibly that brings us to thinking about combining lightweight formal methods and some LLMs. And then this can be tensioned by testing, and by the nature of the testing, obviously the strong guarantee is going to be less strong. But still, it is easy to do. So why not we do this? Basically, in this talk, especially, we focus on executable specification proposed by Memarian et al. Last year. This is basically about writing ghost code in the ambient language. Here, the implementation of C can be seen as a sort of manipulation of the concrete implementation state. So if you run the run the function, then you can manipulate for example, heap or global variables. And then actually the implementation contains a lot of unnecessary details, right? For example, if you think of the hypervisor, then they will sort of deal with some device drivers or low-level stuff. They are unnecessary to specify the intended behavior. And in that sense, what we want to do here is to sort of abstract away unnecessary parts of the implementation, and then you can get some ideal abstract state from the concrete state. This can be done by an abstract function. Then we write some specification to specify what is going to be the intended behavior of the function. Then we compare the result computed from the post state of the implementation. And then if there is a discrepancy between these two, then we can say, okay, the specification or implementation should be wrong. The good thing about this work is that everything is in C. So we don't have to have any additional methodology or framework or infrastructure to achieve this work. This is particularly important if we want to verify the hypervisor retroactively, because hypervisor involves some very complicated C programs or some low-level stuff, and then we cannot deal with nicely in the formal verification even now. Especially we use some pKVM hypervisor, which is an Android hypervisor developed by Google. And then the good thing about this Android hypervisor is that it is widely deployed already. And probably if you have an Android phone, then pKVM is definitely running inside your phone. The goal of the pKVM is to enforce the memory isolation property between guest virtual machines and Linux kernels, so that the guest virtual machine can handle sensitive data such as fingerprints secretly. And then even when the guest Linux Android itself is compromised, we would like to make sure that this fingerprint will not be leaked to the attacker. And in order to enforce this kind of property, it should be sort of a hypervisor. And in that sense, it's going to be a very, runs at a high privileged level under the Linux kernel. And also, everything is mostly written in C, and probably plus some assembly. And these kind of things make the verification particularly difficult. And then that's why we want to consider some lightweight method, especially executable specification for pKVM. Here, for example, if you take some page table, then page tables probably are implemented in three manipulation things, right? So if you want to, for example, if you want to update some page table, then definitely pKVM needs to deal with some low-level stuff like updating some registers or like deal with some device drivers like MMU or such kind of. But in order to specify the ownership structure of the page table or such kind of, these kind of things are unnecessary details. And in that sense, we can think of page tables as a finite maps, like from U64 to U64. And then to this end, to achieve this kind of abstraction, we actually implement an abstract function, which is sort of like walking the concrete page tables, and then builds the finite maps from that. Then we can write, on top of these kind of abstract states, we can implement the specification functions. This is the idea of executable specs for pKVM, which is proposed by Memarian et al. And then in this work, actually, we ask AI to write this kind of specification in C in this style. This is what we did. So now this slide makes more sense to you, I guess. And then now we would like to talk about what we actually did, like what kind of agent we implemented, and then what experience that we have. First of all, the agent that we implemented is called like exec-spec agent. And then this is basically on top of like just a codex, OpenAI Codex, composed of like tons of prompts. It is composed of 300 lines of initial prompts, 10 different agent skills, and then some like knowledge base of how to write some executable specs. The entire pipeline looks like this. First of all, we ask AI to find an appropriate place to be verified. And then we ask AI to actually write the ghost code. After that, we also ask AI to write the test cases and then run the test cases with the executable specs. Then, if there is a discrepancy between the implementation and specification that AI wrote, we also ask AI to debug this discrepancy. If this discrepancy comes from the specification side, then we can just ask them to refine the ghost state, ghost executable spec. But if that comes from the implementation side, then we can definitely need to sort of triage the bug. And then if it's considered to be very serious, then we can just report these kind of bugs to the developer. That is the entire pipeline. And then to achieve this, we have sort of included several important skills. For example, definitely we have to teach AI how to write executable spec or how to write nice test cases. Or possibly, we would like to say, okay, how to build the hypervisor or how to run the test machinery. And also, we have included several artifacts that previously humans developed. First of all, the target binary, like a target Android Linux kernel is Android Linux kernel version 16 with kernel version 6.12, which is the latest version of the Android. And then we have included 3 previously developed artifacts, which is, first of all, manually written executable specifications for the previous version, which is kernel version 6.4. And also we have included pKVM proxy, which is a kernel driver to invoke hypervisor calls from the user land so that we can write test cases as like normal user programs. Also, we have included another machinery, which is called pKVM proxy OCaml, which is an OCaml wrapper to write some test cases in a declarative manner in OCaml. The first thing that we did is to like sort of ask AI to comport these kind of machinery to the latest version of Android. And the results are actually surprisingly promising to me. First of all, what we did is like we ran this agent for about a month with like a single ChatGPT Pro subscription plus a single human, which is me. And then for the first 2 weeks, we sort of tuned the agent. Then after that, we sort of run the agent autonomously for about 2 weeks. Then the agent finally, in the end, like wrote 1,700 lines of 1,000 lines of ghost code and some hypercode test cases. And then more interestingly, they could find interesting bugs in pKVM. So far, the agent found 6 confirmed bugs, and then 4 of which seem to be serious. And then everything has been already fixed by Google developers. Especially, particularly interesting thing is that some of the bugs are sort of a logical bugs, not like a memory corruption, user after free or buffer overflow, not that kind of bugs. And then that is more like a memory breaking some property which is called memory isolation property. Here, pKVM is protecting the property called memory isolation property, which is physical pages are never shared between Android Linux kernel and guest virtual machine unless they are explicitly shared. This kind of property is particularly important to protect the sensitive data because in the earlier slides, I said like, in order to protect the sensitive data, we have to say like, even when the Android Linux kernel is compromised, we have to make sure that this kind of sensitive data will not be leaked to the attacker. And in order to do this, what we want to do, like what pKVM is doing is that like physical pages will not be like shared to the guest virtual machines unless it is explicitly shared. So if you can break this property, then obviously this is going to be leading to the leak of the sensitive data. So let me briefly explain what is page table and ownership so that we can give you some sense of the bugs. So basically, there is a sort of, in the Android, we have physical pages. And then what we want to do here is that like, we have host Android and the guest virtual machine. And then pKVM is maintaining these kind of page tables so that all the physical pages are owned disjointly. Here, host Android uses these blue pages, and then guest virtual machine using these pink pages. And then host Android kernel can map their virtual address to the physical page that is owned by this host Android, but we cannot map this virtual address to the address that is owned by other virtual machines. Okay? And this is basically what pKVM is doing to ensure that like memory isolation can be achieved. And then even when we would like to move the memory to the guest virtual machine, you cannot just copy the map to this one. And instead of doing that, we just first give up this mapping and then add a new map like this. And by doing so, we can transfer the ownership nicely, right? And then what we found is that by exploiting the bug that agent found, like we can create this. We can create a situation where, like, both host Android and guest virtual machine can point to the same physical page simultaneously without some intention or some like accidentally. And then unfortunately, this is sort of still under security review. So in that sense, it might be not good to talk about in detail about this bug. So I can just say this kind of brief overview of the bug. But still, it is particularly interesting because it's not like a memory corruption, but it's more like a logical bugs. And then still, by using some specification, I believe that like this kind of specification can contribute to finding this kind of bug. And unfortunately, this is sort of ongoing work, and in that sense, I have to say like it is unclear whether it is actually it contributes to like finding bugs more effectively or not. I mean, so it is possible that LLMs are just clever enough to find bugs. That might be possible, but still, what we want to say here is that there are some observations that we can defend. First of all, actually, at first I did like, please find bugs in pKVM. Like this kind of thing I first did. And then unfortunately, this doesn't work because it will report so many like a subtle, small issues. And then we will be easily overwhelmed by a lot of like false positives or a lot of like subtle issues. Also, defining the bug like in pKVM itself is very difficult. Especially like, so effectively, when can you say like the ownership like a discipline is violated? This kind of thing cannot be easily detected, unlike memory corruption or segmentation fault, that kind of things. And finally, writing specification itself is a good thing, even when there is like no bug. And especially, I think this point is particularly interesting to us because in the near future, definitely agentic AI and formal verification things are more and more common. And in that future, we believe that what's good for humans and also should be good for like AIs. And then essentially, if you want to apply like retroactive verification to the existing artifact, I believe that like all or nothing verification will not work. And then instead, what we want to do here is to sort of first apply executable spec to like extract the intended behavior nicely while finding some bugs. Then after you have enough confidence about the implementation and specification, then you can move on to more like a formal specification. And more, so in the end, we can probably do some formal proofs by using that specification. And at least what we have is that this works at least for humans. And then on Wednesday, we will be talking about this kind of work in PLDI. So if you are interested in this talk, probably this talk should be also interesting to you. And even though this is done by humans, like a lot of manual efforts, but we believe that this kind of process also can be accelerated by AIs. So I would like to conclude our talk. So what we did is that like we asked AI to write executable specifications, and then that was actually promising because we could find a lot of interesting bugs. And then furthermore, I would like to emphasize that writing executable spec is a sort of a good on-ramp towards the formal verification. That's it. Thank you.
Thank you. So in your work, you had specifications from a previous version of pKVM.
Yeah.
What is your sense of like if that did not exist, would the agent be able to write reasonable specifications?
Yes, I have reviewed some of the specifications, and then some of the specification actually wrong, and also sometimes the porting from the previous version to the new version sometimes wrong. And in that sense, not all the specification looks correct, but still it contributed to finding bugs actually. That is probably the correct story.
Yeah, thanks for the talk and nice work. And what I don't understand is, so you obtain using AI this abstract specification,
yes,
which is executable, and so, but the specification is written by AI.
Yes.
So what does it mean to find a bug in the specification then?
Basically, so the specification is sort of enforced to be sort of mathematical manner, right? And in that sense, like if the implementation is how do I say? Like a specification is sort of a very abstract item of the implementation. And the implementation itself is more like a verbose, and then there are many lines of code. And in that sense, specification itself is going to be sort of the like a compression of the implementation. And then if you ask AI to write this kind of abstract notion of the implementation, probably at some point in the future, the AI will find some paths that there is a sort of discrepancy between the abstract notion and implementation. And then in that case, instead of like just directly fixing some specification or just fixing directly the implementation, we ask them to triage what is going to be the problem. And then through this like a sort of process, if AI is clever enough to like detect what is going to be wrong, then it actually can report some like a sensible bugs. That is the story of this work.
Yeah, I understand the vision, but I don't understand on this particular 4 examples.
Yep.
How did you find them by generating the spec yourself?
I mean, by generating the spec itself. One thing that I have to emphasize here is that like thinking about specification itself is a good forcing function to like find bugs. And some of the bugs can be found through this kind of thinking about specification. But one bug that I have found is like sort of, maybe I need to, one bug that we found is that there is a sort of donation ownership transfer function, which can be transfer some page to another page. But there is another function which can be which can transfer several pages at once to a different virtual machine. And this kind of thing should correspond to each other if you try to iteratively do this kind of batch work, right, by using this hypercode. And then what AI found is that if you try to do this in a batch, you can get this observation. But unfortunately, if you try to iteratively do this kind of work by using the single hypercode, sorry, I'm using some standard hypercode, then there is going to be sort of differences. And then this can be explained by using specification, because we are using the same specification, sort of the same specification for these two hypercodes. And then we will notice that there is a sort of discrepancy between these things by abstracting away some unnecessary things in the implementation. And in that sense, we can sort of extract some common parts of the hypercodes or common sense of the hypercodes. And then by doing that, actually, AI could find some bugs. And actually, I wanted to talk about this bug more precisely and more concretely, but still it is under review. So in that sense, it might be not good to talk about that. Sorry.
Okay. Thanks, Hiro.
Okay, thank you.
The next speaker is Tyler Sorensen from UC Santa Cruz.